Good evening, I'm Bob Watchorn, an old geologist, started in 1968, so I've got nearly 54 years experience in geology and exploration and mining. In the last 10 years, 15 years since I retired, I've turned my eye to research and been using a gradually refined ultra enhancement process, and I've been building a new worldwide structural geology framework using it. Tonight we're going to explore Western Europe to the core mantle boundary, right down at 2,900 kilometres depth. Have you seen in my previous webinars and papers on my website, none of this work's actually been done before, not to anything like this detail. New concepts have arisen from this research. So you'd think that Europe, being the most studied region in the world and the huge volume of great geology has been published, that there wouldn't be much more you could talk about. However, as far as I can ascertain, this is the first detailed structural geology study of Europe that extends from the surface to the core at 2,850 kilometres depth. The current geological paradigms for the formation of Europe, and really the formation of Earth, because Europe's part of Earth, is that the Earth started hot and gradually cooled. Earth started molten with a thin crust which thickened and built up. And plate tectonics commenced as soon as the plates thickened up enough so that they could accrete and get thicker around about 4 billion years ago. Crust's gradually recycling, therefore there's no preserved impacts or anything much older than about, on the surface, much older than 4 billion years, even though the Earth is 4.5 billion years old. The other thing is that coming up through the mobile mantle, there's plumes doing the heavy work of convecting the heat and mass from the core to the surface. And so it's generally touted that the plumes, in association with the ruckling up of the crust, are the main mineralising agents. So anyone who's been to my other 5 or 6 webinars will have seen this one, and I've gradually been working my way round Earth. So the first webinar was on the Yilgarn, and the second one was on Australia's structural geology and mineralisation. Third one was on Africa, fourth one was on Brazil, fifth one was on North America, and this one's on Europe, which really only leaves one to go unless I split it up, but basically the rest of this huge plate, the Asian plate. What I'm trying to do is build a whole framework, a house, if you like, of the Earth. At the moment, this little bit here is how most geologists study the Earth. I'm starting to build a bit for each continent, and in the end I hope to put the whole lot together. So, tectonic geological map of Europe. What's the structural evolution of Europe? These are just questions. How does Europe's structural geology relate to Asia, Africa and North America? We'll try and answer those as we go through. What's the structure of these plate collisions down to 2,850 kilometres depth? If, as most people believe at the moment, is the intense movement only in the crust and generated by mobile forces under the crust? And how deep and extensive is the mid-Atlantic ridge? We'll be able to answer all of those today. Other thing is that the movement on Earth is generally sinistral, so top block moving to the left, and down the bottom here it's moving upwards, so you can actually see the whole of the collision is actually moving in a swirling pattern to the left. So being an economic geologist, I'm really mostly interested in finding more ore. So do the Europe's mines only, they only partially relate to the surface geology? We're going to look at this in a lot more detail. We'll be following these mines all the way down to the, not just down to the moho, we'll go right down to the core to try and find out where the mineralisation originates. I was trawling the web as my want is to try and find good images that I could use. There's just been some fantastic work done in the last sort of 6 to 8 years, and it seems to be accelerating on the Earth and all sorts of stuff that people wouldn't have believed only sort of 10, 15 years ago. And I'm trying to tap into that with my many sources. So the actual carbonate, so carbonates form as a sediment, generally in quiescent conditions, lots and lots of shells and things all piling up. And so whenever there's a ruckling in the earth, they'll get folded up with the sediments and thrust up. So it should be quite a good indicator of structure in Europe. When I looked at the carbonate here, it formed in a great big spiral. Looked here, it formed in a spiral, anti-clockwise spiral. Looked up here, it was an anti-clockwise spiral, and Spain was the same, an anti-clockwise spiral. Thought, oh, that's very interesting. So I thought, in fact, that's exactly what you'd expect if the sinistral movement's moving that way and you've got movement coming this way, is you'd expect anti-clockwise turbulent motion. So there was no surprise there. People might be surprised that's the interpretation I put on it. I'm not quite sure how many people have done that. So I thought, mines generally like tectonic areas, so where do these relate? How do these relate to the spirals? As you can see, they sit right around the edges of them, and very few in the middle. So, well, I don't think they're impacts or anything like that. I think they're due to turbulent flow. So, is there a pattern, overall pattern, a lot more than what you can see in the thrusts in that map further to the activity in Europe? This is seismic, thousands and thousands and thousands of earthquakes generate this, generated each of those little points is an earthquake centre. So we're going to try and find out what's the actual structure of the Africa-Europe collision. So the seismic zones, as we could see in that previous slide, actually form big arcs, which actually didn't seem to relate too much to the thrusts. Now, I don't know how deep these earthquakes are, but they probably go down to 50, 80 kilometres, so really quite shallow. So what might they represent? So just in terms of, just of interest, the earthquakes do sit on these seismic zones a lot more, as you would expect, and they're a lot more evenly spread the further away you get. I've had a bit of questions on how I can get good plans out of, say, a place like Africa, where there's very few seismic, well, not very few, but not as many seismic stations, and quite bland plans. So how can you get something that looks like a MRI scan out of something that's so bland? My answer to that basically is that while there's not that many stations, there's absolutely tens of thousands of recorded earthquakes. And those earthquakes, They cross-correlate them, and they can, seismic guys, geophysical friends can do marvels with that. So I'm not surprised at all that you can get such good information from it. This is my enhancement method. So we'll be exploring the Europe-Africa with Landsat at the surface and in plan and section to the core at 2,850 kilometres depth using my own ultra-enhanced seismic tomography. Quite surprisingly, no one else can produce these ultra-detailed plans, even though me chastising all the geophysicists for ages, saying they should go and pinch some MRI algorithms and then they can do what I can do. And this is despite the abundance of fantastic seismic data. Getting this detail means that you can get huge exploration advantage over people that don't use them. So an example of the detail you get is that's the Landsat, slightly enhanced Landsat image that I started with, where you can see some structure, 50, 60K wide structures. I gradually hone it down until I can see things down to 5K or less. So that star there is the star over here. You see that the star there, unless you're blind, is the centre of an almighty great big concentric ring. That ring actually sits right down in the nose at the bottom of Sweden, which I've called the Acida ring because it sits right on the town of Acida. If I was a betting man, I'd go there and I'd have a look for some shock structures and improve it. This is just a plan of Europe to show the collision front sitting in there, and that's the Acida ring there. You can actually see, slightly see it running around there. And that's the enhanced piece dropped onto the actual map. So putting the whole of Europe on enhancement. Generally speaking, during this I won't be showing the outline of Europe. You just have to try and guess where it is. That's England, that's Scandinavia, that's Europe proper, and that's Africa. So keep that in your memories and you'll be right. So the large Acida rings observed, other rings are there, but the main thing you see is actually very brittle structures all across, and lots and lots of brittle structures that run right from one side of Europe to the other in all directions, horizontal or east-west. So effectively, you're left to wonder how could these structures actually occur in such a mobile environment with all these big thrusts. You can even see large rings out here associated with that centre of that, what I'm calling the Acida impact structure, just for a bit of controversy. I haven't seen these detailed Landsat plans anywhere else, so if anyone can provide me with one, I'll stand corrected. So quickly dropped on the mines and I've drawn a few of the major linears on and the rings. You can see that the mines in particular sit, and we'll see this time and time again, up in northern Scandinavia, sit inside that ring. You can see that they line up with the linears in that direction, this direction. It's not like they're hard to see, these linears. They're great big things thundering across the country. What we'll do is we'll quickly go through maybe the next 10 slides. I'll be going backwards and forwards a little bit on these so you can see the difference between the how the different mining areas form. So each of these little dots is actually not a mine, it's actually a mining area. So this is the gold mines. They correlate with the linears. They also correlate with the outside of rings here. In that ring up there, they correlate with these linears. What I've found is that these, in Australia, the gold mines are on the eastern side of the rings and the big fronts. Here they're on the south side, which is the active side that Africa's pushing into. Australia is getting pushed or is getting pushed into on the east side, so that data is totally consistent. This is copper mines. So the copper mines also sit on the dark zones. They don't sit on these light zones very rarely. They're more in the tectonic disturbed sites. They also they're a little bit different to gold in that they sit in the broader areas of the tectonic ones, whereas the gold sit in the fine tectonic zones. So even now you can start to see from how useful this data is that once you can see the structure, you can then start to put a bit of meat behind any theories you have about how these things form. If you haven't got this detailed structural geology, you're just waving your arms in the air, as I've seen plenty of people do. Now we come to silver, lead, zinc, which is absolutely totally different from copper and gold in where it sits. So there's no mistaking that those things sit on the light coloured areas, and they even in the darker areas they're still sitting on linear structures within it that are lighter, and they sit beside it. So as a lot of the silver, lead, zinc is sedimentary, then these have obviously formed in basins off the main structures. Tin, I started in tin in Tasmania in 1968. A good year underground there, and I always thought it was a bit of a special metal, and I think tin thinks itself is a bit of a special metal. It's very fussy about where it actually sits. So it sits right on ring boundaries, the junction of rings, and where the rings actually are intersected, are like really specifically intersected by linears. Everywhere you see it in Europe. So, I mean, if I was going to explore for tin, there's just heaps of places there I'd be looking for tin. Lithium, flavour of the month. Well, I've lived through the uranium boom when I was probably 8 years old, tin, and then the nickel boom when I first started work, gold, you name it, right through to now. Now we've got lithium is the big flavour of the month, till they find a battery that actually uses something else, and then we've done a lot of wasted work. However, wasted work or otherwise, these are where I'd be looking for lithium mines. So all you do is you say, righto, it's associated with a ring, intersection of a ring and a linear, and you look for all of those places. Rare earths, well, they're slightly the flavour of the month. So if you look at the rare earths, they're generally speaking on the light coloured areas, so they're quite similar to silver, lead, zinc. Not even really sure how rare earths form, so apart from some of them. So they look like they're deposited next to fracture systems, next to major fracture systems, and they are also associated with the perimeter of these rings here and with the centre of this Acida ring. Maybe they're associated with the front of the collision as well. Nickel, first work in Western Australia was with nickel, Kambalda. Nickel mines, they occur wholly within this ring up here. maybe there are other nickel mines all over Europe, but I couldn't find any. So the rare earths and the nickel together, so the rare earths were up in that same spot, and in Western Australia, the rare earths and nickel are associated. Mount Weld deposit up near Laverton and the nickel deposits up there, all associated with the rings of a big ring structure there. Of course, when you think of nickel being associated with an impact deposit, then you think of Sudbury. So if this is an impact deposit, I mean, Sudbury is 200k in diameter, so that little ring there would be Sudbury. I'm not saying that that is a ring, but it does show up as a ring, in, particularly as you get deeper. It doesn't seem like the nickel rings are associated with the collision. Iron mines, they seem to sit out on the flat, more less tectonic areas, and I guess that's to be expected in Australia. They're sometimes in the tectonic areas, but the way they form is in a very quiescent environment, and so they're not necessarily associated with strong tectonic zones. And uranium mines, well, there's only two that I could find, and they're sitting on a lineament, but and on the boundary of a big plate area and a strongly fractured area. I don't know a great deal about uranium, so I've got ultra-enhanced Landsat of Europe and Africa. So I did Africa a couple of years ago, and I grabbed one of those slides and matched it up, well, sort of matched it up with Europe very quickly to see whether the structures look the same. When you look at it on the macro scale, the big structures actually run straight through. Look at it a lot closer in this little area here. You can see the minor structures run through, the north-south one that runs through there, which is this big one that runs right up. These structures run straight through. Sort of verification of the actual method by which I do my enhancements. I mean, if nothing matched, then it means that I'm getting a different result every time I enhance something, which is no good to anybody, particularly if you want to target something. British Isles Landsat, I thought I'd do a local study to see how it correlates with Europe. So once again, that's the starting image straight off Google Earth. Not particularly inspiring. That's the structural plan that you get once you enhance once you enhance Europe. And once again, you can see a large ring sitting on Loch Linne up in Scotland, just near the Isle of Skye. You've got another one in Ireland, Low Ree, or however they say that in Irish, and so you've got that ring there, and then you've got this ring. So if you project the radials to that, they all line up exactly with the centre of that ring. So that big arc down the centre of England is actually an outer ring of one in Ireland. It just shows the rings. If you look at them compared to the geology on the surface mainly trends in this direction, which is actually this overall trend that goes right from the Pacific Ocean across America and right up to the upper north of Russia. That appears to be actually affecting the surface geology. In actual fact, the geology that comes out in Landsat is actually the west-northwest trend, which is the one that traverses the world, which we'll have a look at later. But the geology does have these big arcs here and in Ireland, so it does come through in the geology. We've got the mines plotted on, so the mines actually sit quite happily on the rings here. I'm sure if you looked at it closely, you'd see that they also sit on linears. Once again, I'm targeting a little quick target plan for those who are interested in targeting mainly copper and lead mines, because they seem to behave themselves best there. So you just follow those rings and follow the linears and find a bit of vacant ground where one of these targets is, as long as it's on land. And Bob's your uncle, you'll find yourself a mine. Or not. Now I decided to go down seismic tomography at 80 kilometres. That's the plan I used, so it was a really big plan. And I just took a little slice out of there, where England is, or where Great Britain is, plus Ireland. Better be politically correct here. And these large arcs still show up. The Loch Ree ring, sort of half of it shows up. So according to everything that I've seen around the world, these highly tectonic zones, they're the spots you go and look for mines. Well, one thing about that is that this is the comparison of the linears down at 80 kilometres depth with those at the surface. In the end, I just gave up using I just used the Landsat ones because they were actually so close. So in effect, these linear structures are absolutely vertical. It's something structural geology that you can't get using 3D models. You've actually got to have these structural geology plans to actually make those very important observations. The other thing to look at is this is still a very brittle crust down at that depth, and a brittle crust on which the things you'd expect to happen on a brittle crust still do happen down there. The mines line up with those brittle structures. So it contradicts the theory of a mobile mantle. We should be starting to get into the mobile mantle at this point, but we're not, over which the crust is constantly sliding. I'm sure the crust is constantly sliding, but it's not sliding over a mobile mantle. So this is almost a repeat of the Landsat. Your mines sit on the dark areas, and so I'm sure if this was dry land, there'd be mines all out there as well and up here. So a little bit of targeting down at the 80 kilometre level. Now I've targeted in Australia at 300 kilometres in the Yilgarn, produced a plan back about a year ago of multiple targets, and it's very interesting that a lot of those, or produced that plan about 3 or 4 years ago, that a lot of the deposits that are being found are actually found right where my target areas were shown, like the new nickel deposit north of Perth and various other ones. So these areas would be even better targets for oil and gas. So I did some, because they love antiforms. In fact, that's their life is antiforms. So if you plop targets over all of the antiformal or all the strongly tectonic areas here, that's where I'd be looking for oil and gas. Thought, oh, well, better go and actually, I know there's North Sea oil, so does the North Sea oil sit there or does it sit there? It doesn't, it sits right under where those targets are. Bit of a lead up there. So because that's the area of the prospective area, and it's very clearly defined, I'd be looking down here, down in here, rock systems and depth of water providing. I'll be looking up here, and I'll be especially looking here. You can see that right within that area that I had as a target, there is oil and gas there in the Irish Sea. Proof positive, basically, that these are valid targets. We're going to look at the seismic tomography of Europe from 100 to 600 kilometres depth now. Find the ultimate source of the mineralisation. We'll track the source structures under Europe right down to the core and just see if they line up with the mines on the top. So these images, they're the ones I'm going to use, 100, 300 and 600. They are produced by these people, and the geophysicists. Take my hat off to them because they go to lots and lots and lots of trouble, iterations and just lots and lots of mechanical, mathematical work to actually get these images. Absolutely something I couldn't do. However, I can get those images and I can make them into something that's so far the geophysicists can't do, so they've got a bit of catching up to do there. So these images were struck by the fact that it's a very big, large, curved area, and it seems to have a ring of around each one at the various depths. And I'd already done a study up from the Caspian Sea here right around to Fennoscandia, in which that part, this is actually halfway between this one at about 200, 250. That had lots of little rings, about the size of the rings in England in it, but it showed up as half a section of a big ring. So I think these large fast crust, it's a remnant cratonic material, actually the core of the gigantic rings. It's just you're down 100k now, just the mines line on it. That's the front, got from the enhanced stuff, but it shows up quite well there, with the mine sitting in the front of the African, the bow of the African ship hitting Europe's about here somewhere and doesn't seem to be getting much further, but as you go deeper, this front or shocked area actually seems to be going out further. A little bit like the bulb on a huge tanker ruckling up the sea before the bow gets there. So that's the enhanced, quite a quick enhanced one of it at 100 kilometres. Just separated that out into the domain, very strong shear zone, for want of a better word, domain. Lots of linears which don't show up particularly well. I've dropped the mines onto them. So I'm not going to make too much of a deal of it, but that actually follows that linear. The thing that struck me was that the coastline of England and then Fennoscandia, like the Baltic Sea, and that you go from higher country to low country here, and that so that means that all of this has been dropped down. Well, that's my reading of it. And might also explain why, even though you've got the rings lining up on these big major structures coming down, why they suddenly stopped there. They stopped there, I think, because the country's been dropped down, like the west coast of Western Australia. 1,600 kilometre Darling Fault just drops the country down about 20 kilometres. Same thing's probably happened there. Go down to 300 kilometres. The front of the collision now moved out to here. That's about all that's to be said for that one. Quite hard to actually get a decent plan off that, and I sort of ran out of time on a lot of this, but you can see a broad front there in between those two lines. That's the front of the African continent, sitting just north of where it is. That's at the surface. This is down further, and then maybe that's the African continent down further, but that doesn't. It shows here when you look at the sections, and that this is the big bow wave of the African continent. You can see once again the ring up here, which seems to have been going right through. The nickel and that are all associated with little rings and bigger rings. See smaller ones down in there. You can see a nice serrated, I guess you would say, or linear system running through there, and another one running straight up and down. If you look closely, you can see heaps of stuff. Just drawing up what I just said. If you really want to look at these, then I'll be presenting I'll be putting it all together in a paper which I can give out afterwards once I've done it. So now, as we get down, we're actually really starting to see the structures starting to coincide or correlate with the actual major structures that you can see. These were quite plain, these structures. As you can see, the nickel mines, while they are associated with that ring that sits in there, they also seem to run down this north-south structure. Interestingly, that north-south structure is actually the northward promulgation of the East African rift structure, or the African rift structure, heading right up through Europe. Work that one out if you can. You can also see that down here they sit in the ring structures and around the ring structures. And once again, there's a sharp cut-off of the mines along there. So mines the land in this area, I reckon, is actually probably downwarped or dropped down. I'm doing a webinar on European civilization and how it started, and my premise is that it started with mining. And so I did the same exercise as I've done with the mines with the henges, or the ancient Stonehenge type things, and lo and behold, they, even much better than the mines, actually follow the rings and the linears. And I found that, and effectively, so maybe following where the ancient, our ancestors actually built their henges might be a good way to find mines. Maybe if civilization did start with mining, then these guys that were building these actually were mining at the time. So it's probably a good geochemical plan of Europe, for copper mainly. So back to joining Africa and Europe together. I can't see much there effectively, but you can see the major big structures running right through. You can see these, so mainly the northeast and the northwest structures running right through. Once again, these were done a few years apart using different data sets. Down to the bottom of the seismic tomography that I've looked at. So now the front of the collision is way out up around Norway, out past Britain, and so basically encompasses all the mines now, for what that's worth. So you can, when you look at it in detail, you can see this big world-girdling structure, which we'll see in a slide later, seems to get dispersed when you get up near Britain. This is the East African rift structure, and strong linears running through, still almost the same directions as we had in Landsat at the surface. Plot the mines on. It's a little bit hard to see on this one, so we won't dwell on it, but they do follow the linears. Well, they're aggregated mainly in the tectonic areas and following these linears running north-south at this point. And like so England and Spain did a bit of an exercise to see what the dip of the front was in front of Africa. So the African continent actually is almost vertical down here. Not doesn't even go out that far, but the disturbance goes way out in front of Africa. And it's pushing up the Eurasian Greenland plate, just as it pushes up this end of the European plate. Well, European plate, and this is all one plate really, but this part is the disturbed part. So now you can't do this sort of exercise. As I've said a couple of times, you need real geology to do these real geology type exercises. So I think it's long past time that people actually got serious about the geology under the earth and produce these type of plans so they can actually do real geology instead of 3D improvisations of geology, which really, most of them just say how the heat came up from the core to the top and they assign them to plumes. So talking about the core, we go right down to the core mantle boundary at 2,850. This is the image I used. Now have a look at this big plume, for want of a better word, of hot rock, and it's going off in the same direction as this big linear structure or zone up here, as is the one here. I have a bit to say about that later, but I believe they're actually caused by the compression from the Pacific plate pushing up that way and pushing Africa and America together and squeezing it. And I'll show you what I think happened. So I took a slice of, just took a snip of the seismic tomography up here, same routine as before. And well, to me, it's not a surprise because I've seen this in the last 3 webinars I've done, but for those that haven't seen the webinars, it should be a surprise that the core has got outer core has got exactly the same structures and radially exactly beneath where they are on the surface as what you see in Europe above. So you've still got that northwest trending structure, you've got a northeast trending structure there, the strong tectonic zones still in exactly the same place. So that goes right from the core right to the surface, vertically. You can sort of see it in this, this is just a compilation, so you can see the strong structures in the Landsat, see the same strong structures in the, not quite so strong in this one, but you can still see strong structures down at 100K, 600K, run out of space. You can still see the same strong structures, north-south ones, northwest ones, maybe not the northeast ones quite as much, but they're still down there, sitting in there. And down at the core mantle boundary, they're still there. And what's more, they're still in the same spot, they haven't wandered all over the place. And that's the main reason I believe the Earth's lithosphere is rigid, because how in the heck could you actually have all those structures going straight through the Earth with if it's moving all over the place? They'd be 1,000 kilometres away at the top. That was just, these are just isometric projections showing the same thing. So I think the very much a challenge to explain these with current current plate tectonic hypothesis. Equally as much of a challenge to explain it with a rigid lithosphere. The movement of the plates up the top, how in the heck can you get it with a rigid lithosphere? So my concept at the moment is a lithosphere consists of shuffling brittle blocks that can still move and jostle together, but they move from top to bottom around above the liquid outer core. But I still can't figure out how the whole block can move at the speed the current crustal surface is moving. For them to move like that, there's got to be a tremendous amount of mountain building going on and crushing. So if the excess lithosphere is planed off, is the excess lithosphere planed off by the hot outer core and digested? And we'll have a look at that a bit later. So we're going to have a quick look at the European seismic tomographic trevises. So we know the geology of Europe, big nap thrust structures there. They show up in my tomography. In fact, they show up fantastic in my tomography. This area here is just this tiny little area up the top. You can see that they show up there. Why I think the front of Africa sits there is that you don't see Africa sitting all the way out here. It sits pretty vertically under Europe. This is just an enlargement off the big ring that goes right around to the west of America. It's another seismic tomography section. So you're looking at Europe, that's east looking up, and this is Africa, the dark bits, and this is the front sticking out and the front sticking there, and this is probably the front that we've been looking at here. Show this mainly to show that the big linears that come through in the Landsat, actually you can see them running right through the lithosphere. They're not, they don't just stop here and then all of a sudden it's just a mobile mantle. Like there is no mobile mantle, just pure and simple. We're down 1,000 K here. This is another one, almost through the same section, but it goes right down to the core. Reasons of space, I cut it off at about 2,000 K down, but the different way of enhancing that I did still shows the pushing structures from Africa, but I'd say that these are the actual stress lines of the structure, that the actual stress lines are, so this is all getting pushed up all the way across basically to the mid-Atlantic ridge. That's Iceland there. You can actually see the mid-Atlantic ridge there, all of about 100 to 200 K wide. No evidence of it out either side. That's interpreted, that's the Landsat that we saw, and you can see that a lot of these structures actually come straight off these major structures. Suggests that major big tectonic zone is actually dipping to the north. And a lot of other structures are dipping vertically or steeper. So there's two conflicting things here. You've got one lot of form lines, I guess, of stress actually are pushing up, and the ones on the previous ones that we saw, they follow this line here, and they're pushing to the northwest. This is the seismic tomography at 200 K depth. Just I keep harping on about these almighty great big linears that run right across from Europe, across America and right through Pacific. Other ones at different angles that go right up here. And this main tectonic zone that goes right up through there. Other thing you can see here is the mines, which are the yellow, they actually follow these big rings. That's the big ring that I was talking about up in Russia. The mines form a big arc around that. This is a image of how still at 200 kilometres depth, same image as before, as how I believe the big plates are moving. So you've got Antarctic, Australia, Africa plate all moving to the north and probably to the northwest slightly. We've got this plate probably relatively stable. America, very stable plate. America's very stable because it's getting pushed from the west by the Pacific plates. The Pacific Ocean's actually the thing that's expanding. None of this is expanding, and this plate's actually getting pushed to the west, and so there's a huge big compaction or compression zone running right up here. I've actually done a seismic survey across there, and that shows up as a very big compression zone, as does this one in America. And the other thing is that whatever way you look at it, the Mid-Atlantic ridge is very narrow. Mid-Atlantic ridge there, that's the plume, but that's just hot rock, not anything that's moved, because the big structures go right through. America's getting pushed this way, Africa's getting pushed that way, and it's all compressing. So it should, theoretically, there should be big mountains. They get knocked off by the ice, but as you go down, what happens to when they go down the bottom? This slide really just shows the rigid crust in all the sections, in all the areas I've seen across the Earth. Big structures going right down to the core. So this is how I believe the Earth retains its mass balance. I think because so Africa's getting pushed this way by the Pacific plate. Pacific plate's pushing America. That's the big subducted zone. So the other side of America's there. So America's underplated by Pacific crust, which theoretically should have lifted this way up into the air. But as it's heading down, it's actually pushing itself down into the outer core, which is nickel iron. The core is nickel, it's differentiated. Interestingly, only really recently discovered that the core moves that way, the outer core rotates in the opposite direction. So in actual fact, the differential motion between the lithosphere going in this direction, the outer core going in that direction is actually probably quite a lot. And if you think of plasma welding, effectively 6,000 degrees it'll just totally obliterate any lithosphere that gets poked down into it. So I believe that's how the forces in here are dissipated. So differentiation, so silicon, aluminium going up, magnesium, iron staying in here, iron, nickel, and the nickel's differentiating to the bottom. So seismic stuff says that the nickel core's building up, and we also would assume, getting cooler again now, that the lithosphere is building. So we've got a lot of new geological paradigms for the formation of Europe. They are that the Earth started cool and gradually heated up. The original constituents at -100, space temperature, and only gravity to pull them together. Didn't start as a big atomic bomb. Earth started rigid and only started breaking up in a fairly minor fashion, perhaps in the Proterozoic. True plate tectonics only commenced relatively recently, like I'm talking maybe only 1 to 2 billion years ago, and no evidence whatsoever of lava lamp type plumes. The heat transfer, all these structures going through right through to the core says that it's got to be by in situ replacement. Planar and ring structures down to the core correlate with the surface mines, like they correlate fantastically with the surface mines, enough that you can target on them. And superheated fluids from the core with the lithosphere getting scraped off differentiation. They scavenge and deposit these minerals as they ascend. Thank you very much for your attendance at this webinar, and I'll throw the room open for questions. Thank you very much.